So we have a problem here that asks us how many of the following molecules are polar, and it gives us 5 different molecules. We should approach this problem by drawing the Lewis structure for each molecule, determining the molecular geometry, and determining if there is a net dipole. We know that if there is a net dipole on the molecule, then it will be polar, and if there is no net dipole, it will be nonpolar. Let's start by drawing the Lewis structure for SO3. First step is we need to go to the periodic table and determine how many valence electrons will be in this structure. We know that sulfur will be the central atom because it has the smallest electronegativity, and that there will be 3 oxygens around it. Let's start by putting bonds to each oxygen and then giving our outside atoms octets. Now let's count to see if the number of electrons in our structure matches the number of electrons that there should be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 pairs times 2 electrons in each pair gives us 24 valence electrons. We can continue on this structure to give sulfur an octet by showing resonance between the oxygen atoms. There's going to be a bond here, partial bond there, 2 electrons left, 2 pairs of electrons left, bond here, partial bond, and 2 pairs of electrons left on that oxygen, and it will be the same thing on this final oxygen. Now our central atom has an octet, and all 3 bonds, all partial bonds, are equal. Now let's determine the molecular geometry for this molecule. We have 3 domains, 1, 2, and 3. All 3 domains are equal, and there are no non-bonding domains. So we have a sulfur here, oxygen, oxygen, and oxygen. All 3 domains are equal, and this is going to be a trigonal planar molecular geometry. Oxygen is going to be the most electronegative, so there will be a partial negative charge on each oxygen here, and a partial positive on the central sulfur atom. The rule states that if all domains are equal, the dipoles will cancel and the molecule will be nonpolar. The dipoles in this molecule will go towards the oxygen atoms because that is where the partial negative charge is. All of these dipoles will cancel because all the bonds are equal, and this molecule will be non-polar. Let's go back up to our problem and write that above this molecule. I'm going to put it NP for non-polar. We need to do that for each of the molecules that we are given. Let's come down to OF2. I've already drawn the Lewis structure, but let's check to make sure I've done it correctly. I've calculated that there should be 20 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pairs times 2 electrons in each pair gives us 20 valence electrons. That is correct. And as you can see here, there will be 4 domains. 1, 2, 3, 4. 2 of those domains will be non-bonding. 4 domains will give us a tetrahedral domain geometry and a bent molecular geometry. fluorine is the most electronegative in this molecule. So the fluorine atoms will have partial negative charges, and the oxygen will have a partial positive charge. The molecular geometry is bent, and we have two non-bonding pairs here. The dipoles will move towards the most electronegative atoms, and they will not cancel. The rule states that if we have four domains, two of which are bonding and two of which are non-bonding, the dipoles will not cancel, and we will get a net dipole in this direction, which would give us a polar molecule. Let's go back up and write that above the OF2 in our problem. We're going to put a P for polar. Next, we have BeCl2. I've drawn the Lewis structure, but let's check to make sure I've drawn it correctly. I've calculated that there are 16 valence electrons. We have 1, 2, 3, 4, 5, 6, 7, 8 pairs, 2 electrons in each pair, 16 valence electrons. There are 2 domains, so we will have a linear domain geometry here. Chlorine is more electronegative than beryllium, so the chlorines will have partial negative charges, and the beryllium will have a partial positive charge. That is our molecular geometry, and there will be dipole movement towards the chlorine atoms here. And since this is a linear molecular geometry, it is easy to see that these two dipoles will cancel, and we will be left with a non-polar molecule because there is no net dipole movement. Let's go back and write that on our problem, NP for nonpolar. Next, we have CCl4. Calculated that there are 32 valence electrons, but let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bonds gives us 32 electrons, so that would be correct. We have 4 domains here, and all 4 domains are equal. That will give us a tetrahedral domain geometry and molecular geometry. Chlorine is more electronegative, so it will have partial negative charges. And carbon will have a partial positive charge. We will have equal dipole movements towards all 4 of the chlorine atoms in this molecule. And the rule states that if all of the bonding domains are equal and there are no non-bonding pairs, the dipoles will cancel and there will be no net dipole. So we are left with a non-polar molecule. Go back to our problem, put an NP for nonpolar, and we are left with one last molecule, which is O3. O3 has 18 valence electrons, but let's check to make sure I've done it correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bonds gives us 18 electrons. And because this is oxygen, we need to get a octet on that oxygen. This structure will have resonance in order to get that oxygen atom to an octet. We will have equal bonds between both outside atoms and the central atom. So those 2 domains will be equal, and we'll be left with 1 non-bonding pair. So we have 1, 2, 3 domains. So our domain geometry is going to be trigonal planar. However, because one of those domains is a non-bonding pair, as you can see here, the molecular geometry will be bent. We have this non-bonding pair here. Because of this non-bonding pair, the central atom will have a very small partial positive charge, and the 2 outside atoms will have partial negative charges. This means that we will have 2 dipoles going towards the outside oxygen atoms, and it is easy to see that these dipoles will not cancel, and we will have net dipole movement in this direction, and this molecule will be polar. Let's go back to our original problem, and write that it will be polar. The problem asks us how many of the following molecules are polar. Let's count and find out. Nonpolar, we have one polar, so that's one. Nonpolar, nonpolar, one last polar. There we go. So we will have two polar molecules and 3 nonpolar. So 2 polar will be our answer.